This conference will now be recorded.
Perfect. All right. Hello, everybody, and welcome to SFPUG October Meetup. I'm your host, Catherine Saar. Before we begin, the meeting is being recorded and will be posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on when speaking, will be part of the recording. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we do recommend, you can use the raise hand function to join the queue. If you're using an older version of the app which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they will add you to the queue. The organizer will let you know when you're next in the queue, so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we're monitoring during the presentation. SFPUG, Bay Area Postgres, is a PGUS-affiliated user group, and I am a volunteer for PGUS. SFPUG is sponsored by PGX, and I work for PGX. And thank you for joining us for Vindicating ZFS with PostgreSQL, Unleashing the Power of Scalability with Federico Campoli.
Good, thank you very much. And yeah, I shortened a little the title on my slides just to avoid to spill over the entire presentation. But yes, it's still vindicating about the ZFS and PostgreSQL. So let's start with this presentation. I've given this thing several times, and people have been quite interested in how this thing has been unleashed and how the entire thing about ZFS can improve Postgres. Quick few words about myself. I was born in 1972, despite I look younger. I started with the IT in 1985, mostly because of the movie Tron. I think it's still one of the best movies on the digital universe ever made. I fell in love with PostgreSQL in 2006. Also, in 2007, I organized the first PG Day in Italy. I'm from Italy. And PostgreSQL and FreeBSD tattoo on the right shoulder. At the moment, I have this hoodie, this PostgreSQL hoodie, so I cannot show you, and it's also pretty cold, so please believe me. And I work as a freelance BDBA, mostly on PostgreSQL, basically. If you want to get in touch, this is my LinkedIn page, this is my Codeber page, Blue Sky, and Mastodon. And also, this is my blog. I haven't updated too much on my blog, but I always say I promise myself to add the new stuff. Hopefully, I will find the time for writing. It's been quite difficult for me recently to focus on writing long posts, but I promise at some point I will do it. But there are a couple of interesting posts that may be related with the talk of today. You may want to have a look anyway. In particular, discussing about the Linux memory and how it relates with the with PostgreSQL itself. Little disclaimer, this talk is based on real life experience. Basically, I think it was 3 years ago, I worked for a company. Obviously, I cannot disclose the name. This company had a pretty big database, and they had serious issues about the expensive, spending a lot of money on the storage. They were on a cloud provider, so they the database costed a lot of money just for the storage. All the tests we are doing, I'm showing here, are just reenactments. They differ a little because I also use a different cloud provider. I will also have some consideration about the cloud provider at the end, because it's quite interesting how this thing changed across the different cloud providers. There are a lot of topics not covered by this talk, and obviously, if you think about using ZFS for your needs, always do your test before going to in production. Do not take this as a static idea that will work, always will work. There's obviously things change and depends a lot by the distribution of data, the workload. So it's just, this thing is just based on PG bench, basically. So let's give you some context initially. This is the agenda for today. So some context, the key master and gatekeeper. If you love Ghostbusters, you will know what I'm talking about. Some tests, and wrap up about the final considerations. So some context, very simple. This story is do you hear about is true. The names have been changed to protect the innocent, basically. Dragnet, a lovely series. So, long time ago, there was a startup in a far, far away galaxy, and they were running Postgres on someone else's computer, also known the cloud. And this computer, this database was misused, abused by the developers. Basically, this database I've seen several times because it wasn't the first time I worked for this company. And this database started small, it became slightly bigger, and then it just exploded. We are talking about volume in the range of tens of terabytes of data. That was the size, and that was the reason of cost of the entire thing. And in fact, it ended bloated. Doing maintenance, it was basically a nightmare. Even with the PG repack in place, it was basically very, very, very complicated. So at the end, they called the DBA, me, and as usual, the DBA approached the problem delicately as always. So this is Sparta. I started screaming and kitching and talking about things that were just not correct on the configuration. So what are the problems between Linux and PostgreSQL? This is a very bold statement. I agree. Postgres and Linux are not friends, and there are reasons for that. Why Postgres and Linux are not friends? Because basically Postgres is multi-processing, not multi-threaded. Block size is 8K, and normally the shared buffer is supposed to be one big shared contiguous memory segment allocated in memory, and also consumes a lot of memory. But what does it think the key master about that thing? Well, the gatekeeper, sorry, she's the gatekeeper. So, well, Linux implements the NUMA, not uniform memory allocation. So normally the memory that is you may think as a contiguous segment in memory is just scattered around the RAM. And then on x86 architecture, the max file system size, the max file system block size is 4K, so half of the Postgres block size. So normally the page, the Postgres single page, it fragments into physical pages on the file system. And there's also one thing about the dirty flush. When the kernel flushes on disk without any, when it started the synchronous flush, it blocks the I/O. So Postgres, it stops working. I had a customer a couple of days ago that called me because a monitoring system was just freezing their databases, and they had no tuned this thing. and they believed it was Postgres that was not copying. No, it was just Linux that was doing Linux. So, and also, yes, the OMM killer. If under the normal circumstance, on the normal configuration in Linux, if one process consumes too much memory, it may be killed. And this is, on a database server, this is very likely will be a Postgres process with all the bad that this may cause. Crash recovery, basically. So, but they can be pushed together. And how do we do that? Well, in PostgreSQL, tuning the max connections and the usage of huge pages, in particular if we have a large shared buffer, may be critical for improving things. And also, do not oversize the shared buffer. This is one of the blog posts I mentioned at the beginning of this presentation. And if you look at my blog, you will see why a large shared buffer can be regression rather improvement. It can cause regression rather improvement. On the Linux side, disabling the NUMA, so basically tuning down the kernel for not using the NUMA, and also configure and use the huge pages, because the huge pages are an extra complication for being used. It has to be configured on Postgres, but also it has to be allocated in Linux. So it was like before the improvement of the memory allocation with Postgres 9.2, where we had to tune the kernel SHM max for having a larger shared buffer. Huge pages works in a different way, but guarantees that the shared buffer stays into one single segment. And also configure the VM dirty ratio and disable the memory over commit. Also, I remember Christophe, that is here, mentioned several times, the memory over commit for the Postgres point of view is just a bug, so disable it. And on supported architectures, set the file system block size to 8K. IRM64, for example, it allows to have the file system to larger values than the 4K, or use a file system more flexible like ZFS. And this is the thing about we will see tonight, for me is tonight. So let's talk about the file system, the native file system first. I will focus on XT4. XFS is similar in terms of configuration, but this thing it will talk only on XT4. Because the XT4 was the file system we used at that time, so I will just limit to that thing. But I reckon it may be interesting to also compare with the other native file system. Well, the XT4 as a default is not exactly friendly from the Postgres point of view, because the access time update to any file on the file system is just a waste of time for the CPU. So disabling the A time with the option no A time, and also implies the no DIRA time, and improves the access and the writes, just because there's less thing that the operating system has to do when access the files on the file system. Disabling the barriers may improve the speed. I've seen this thing as a trick for the old-fashioned Fusion IO cards. That things where basically ignoring completely the kernel barriers, the write barriers, and the speed was dramatic compared to the corresponding NVMe at that time. I'm talking about 2012 as a time. Is not suggested to do that thing on virtual file systems. So be careful about your environment. If you are on bare metal, barrier 0 may be an idea. Setting data write back, set the data journaling write back mode, so less time spent to write meanwhile the data is being written onto the journal, is similar to the synchronous commit in Postgres. This is the corresponding for the file systems. But let's talk about ZFS. ZFS is the last word, is described as the last word in the file systems. It's described as stable, fast, secure, future-proof, and include pooled storage, copy on write, snapshots, data integrity and verification and automatic repair, RAID Z, so you can basically build up a RAID configuration out of your volumes directly from the ZFS configuration, instead of using, for example, the MD admin in Linux. And up to 16 exabyte file size. I have no idea how to write this number. And you can set up to 256 quadrillion zettabyte storage with no limited number of file system sets or files. It's pretty impressive, but also it has a license that is not compatible with the GPL, so normally is not present on Linux. You have to install as an extra module. Is memory greedy. This is another problem with ZFS. You may need to have a very extra large machine to get the best performance from ZFS. It is not designed for hosting the database of the cooking recipes, basically. And maintenance also requires attention because it has to be defragmented and trimmed over time. Is not very efficient in writes. We will see this in particular on the tests. And there may be some bugs that may cause data corruption. In that case, this bug causes the zeroing of files when using a particular configuration for the RAID ZFS. I can't remember the correct bug, but it wasn't exactly nice. So like anything, any software that is not immune to bugs, even this mature file system may have some pretty horrible bugs. So always be aware that nothing is perfect. Advantages. Another advantage of ZFS is that the options, most of the options, can be changed dynamically. So you don't have to unmount and remount. Meanwhile, in XT4 or XFS, you have to change the entire thing, the settings in FTab, and then you need to unmount and mount back the file system for applying the changes. And that means shutting down any process that is using the file system. In ZFS, things can be changed dynamically without doing anything particular. And so A time can be turned on and off. The record side can be changed. So the record side is the block size. I also love ZFS because the feeling is to have more to deal with the database rather than file system. Record size and also the compressions can be enabled. Obviously, all these things apply to the new data. Written. So if I change the record size to a different value than 128K, this thing will change only for the new blocks allocated, not the previously allocated blocks. And similarly, the compression. Also, the log bias can be set for giving hints to the operation of the ZFS. Log bias is similar to the is a log where the ZFS writes the intention of the writes over time, and then is used for determining preemptively how the data is being accessed by a process. It's quite clever. Honestly, I never been used successfully in using it at the maximum power, but in some way can improve easily. So basically, also, because ZFS is a module, is a kernel module, is not native in the kernel, it's possible to preserve the configuration into the module file configuration file. So is in etc modprod.z zfs.conf. And the parameter can be set here, but also can be dynamically changed by just echoing the value into the corresponding parameter into the sys module ZFS parameters file system. So it's pretty, even pretty dangerous, this thing, because you can screw up the entire operation by just changing the setting in the wrong place. So let's do some tests, and let me talk about how these tests have been done. So first of all, I made this test on Google Cloud Platform, so GCP. The original configuration, the original experiment, because it was a giant test at the end, with my recommendation at the end, that I have no idea if that been implemented. That thing worked on AWS. And there is one important thing about it, one important difference between AWS and the GCP is how the files, the file system, the volume, the storage volumes are managed and allocated. But I will come later to this thing. So I set up this machine with an E2 IMM, with an SSD on data area and WAL area, SSD on a table space for XT4, another SSD for ZFS table space, and one final SSD for the ZIL, the ZFS intention log. I used this thing as an example, but it didn't change too much in terms of configuration. So hardware, quoted hardware, is still somebody else's computer, but it's still a sort of hardware. E2 IMM8 with 62 gigabyte installed RAM, pretty large, but not so big. 8 processors, AMD PIC 7B12, separate volumes for the WAL area, data area, and SSD. XT4 tablespace on persistent disk SSD, tablespace on ZFS, and ZIL on ZFS, on SSD. Everything on SSD. I separated also the WAL area from the data area, and I also separated the data area from the table spaces where I'm running the test. Because in this way, I would completely detach any IO into the Linux kernel from the normal operation that Postgres does, like checking the commit statuses or writing on WAL. So I completely isolated the writes for the data files into dedicated table space. And no swap area, the machine had a lot of memory, so there was no real reason. Everything was running on top of Rocky Linux 9.3. So kernel configuration, I mentioned before how to set up the kernel configuration. Well, first, dirty background ratio. I would like to 5%. I like to have background writes all the time from the kernel cache to the disk. The dirty ratio set to 99, it means synchronous flash, blocking flash, only when the entire kernel cache, almost the entire kernel cache, is written by dirty pages. So only at gunpoint it will flash synchronously. Overcommit memory disabled. Overcommit ratio to 100%, so it means every single process can request the entire amount of memory if necessary. Swappiness set to 0, but it won't be necessary because there was no swap, but just as for completeness. Postgres setup. At that time, the tests were on Postgres 16.2. It may be interesting to run the same tests using the Postgres 18 and the async IO. I didn't got the occasion and time for doing that, but I might write a blog post about that. It may be interesting. Shared buffer set to 1 gigabyte, working memory to 400 megabyte, max connection 100, and max WAL size 5 gigabytes. Give some breath to the checkpoints triggered by the WAL switches. Using PGBench, using standard transaction type TPCB, a scaling factor 500, 500, yes. And then this means it will create a table with 50 million rows on accounts, 500 rows on branches, and tell us 5,000 rows, sorry. And the number of clients for my tests were 50. One thread, and duration for each test 120 seconds. Also, no foreign keys. I didn't want to have any extra work imposed on the CPUs. I just want to measure the I/O and the performance of the I/O, and initialization of the tables from scratch at each test. Because it's also interesting to see how the initialization performs on the different file systems. So let's start with the XT4. Initialization generates the data, and this thing takes around 66 seconds, no, 85 seconds, that's it, and generates 7.4 gigabyte of data. Not bad. And then I start PGBench, 120 seconds or 2 minutes, and the entire thing returns me about 4.9 thousand transactions per second, so 4,900 transactions per second. Without the connection time, the connection is persistent, so everything is fine. Same thing with the no A time and no DIRA time enabled. That was XT4 without any optimization. Optimizing the with no A time and no DIRA time, so less work for the entire thing. It takes less time for the operation. Space is still the same, and the transaction per second increases slightly, 5,300s instead of 4,900s. Also, some improvement can be done by adding the data write back. Adding the data write back, it shrinks down the initialization time and slightly improves the transaction per seconds. And now it comes our friend ZFS. Let's initialize this thing, and then we start seeing something that is not nice. 90 seconds instead of 85 seconds, slightly slower than the not optimized XT4. But when we go for PGBench, we will see that the transaction per second is 1700s. Is just horrible. What when we first had this result, we said, okay, ZFS, he had a bad reputation. It's true that he has a bad reputation because the transactions per second are not comparable to the native file system. At that time, it was also more dramatic because of the storage, the underlying storage. In that case, it was incredibly favorable because the storage on GCP is more similar to disk rather the software implementation on AWS. And then we started trying to optimize these things. So we turned the A time off, and there was a slight improvement in the generation, slightly better. No, it's even worse than the other one. And the transaction per second improved slightly better, but it's still, what the hell, it's still no good. So we thought, why don't we turn on the compression? Maybe having less data to read and write, it will improve things. And then turning on the compression on, still with the A time off, with the LZ4 compression, the native, the default, well, the initialization dropped under the time of XT4, in that case, in this test, and also the space improved sensibly to less than 1 gig instead of 7.5 gigs. And at the end of the story, after running the test with this thing, well, now is much, much better. Because we have, well, we still don't have the same performance of XT4, even with no tuning. XT4 beats ZFS, but the space gain is pretty important. We can have a smaller file system for holding the same data. So we tried to optimize also the record size. The record size, for example, at 16K, the space used increased a little because it's storing more data in chunks smaller, so it fragmented more and more. It's less effective for the storage, for the compression. But also, and this is a case of GCP, on AWS, the performance was almost the same of the not optimized, slightly worse than the not optimized. On GCP, the performance is even better than the XT4 optimized. Why? Because the storage is more efficient, is more a real storage rather a virtualization in GCP, differently from AWS. And plus, I suspect that GCP does not set aggressive throttling on the I/O differently from the from GCP from AWS, depending obviously on the storage. If I correctly remember, at that time we used an IoT2. I can't remember the correct names, but it was pretty expensive, so it was the best possible file system used, and it was still ZFS was performing worse than the counterpart on GCP. But how can we improve even more things? Well, we can set some of the modules parameters for ZFS. For example, we can disable the prefetching, we can disable the cache flush, and we can also, and this was quite critical, setting the IRC, the adaptive replacement cache. This is a name that was in the Postgres 8 will remember. The adaptive replacement cache in ZFS normally has two different values, minimum and maximum, but the ballooning of this memory, it costs time and CPU. So setting to a single value, assuming that Postgres will consume memory and will require enough memory, it may be an interesting timeout. And also the 3xG timeout set to 1 to have a sort of asynchronous flush on disk. It may improve the entire operations. And also using the ZPool. Well, in my tests, using also the ZIL. This is the ZIL I mentioned before. So I dedicated just one SSD for the ZIL. It gives some improvement for the generation, but not big improvement in terms of the benchmark. In fact, is even slightly worse compared to the previous configuration. It depends a lot by the underlying data. So in that case, 6288, 6268 is basically not significant. They are exactly the same value. So there's literally no improvement at all. And let's see now some space usage comparison. Obviously, all the XT4 will use always 7.4 gigabyte, whatever we add to set. And also ZFS with no tuning will use a same storage. But when we turn on the compression, we can gain a lot of space. And that's important because if we rely on top of large databases that maybe need to be optimized for reads, and the smaller storage may improve the read because there's less data to move between the disk and the memory, and then it decompressed, uncompressed transparently. This may be a win-win situation. But always, as I said, always do your tests. In terms of load time comparison, we see that the sweet spot for the load time comparison is ZFS no time with compression LZ4. 52 seconds compared to the others. The slowest in terms of time is XT4 with no time. No idea why, but I would expect a smaller value anyway. In terms of latency, we have the sweet spot is with the ZFS NoeTime LZ4 record at 16K. The record at the default 128K, it gives a lot of space gain, but it doesn't give complete performance improvement. And finally, the transaction per second, the larger is better in that case. So basically, we have XT4. The best configuration is this one. They are basically similar, but in any case, the XT4 NoeTime with write back get the best performance for XT4. In terms of LZ, in terms of ZFS, the best performances, whatever we are using the ZIL or not in that case, is with the compression LZ4 and the record size at 16Ks. I have an idea why 16K is the sweet spot, because the block size in Postgres is 8K. So 2 block size can sit easily in 16K. 128Ks can also store more data, but you have to decompress more blocks for extracting the same value. 2 blocks instead is a good compromise between compression and also waste or read for reading just one of the 2 blocks. So 6 minutes left. So we are at the wrap up of this thing and also the consideration for this thing. ZFS can achieve good performance despite a bad reputation. It depends a lot by the subsystem. I will tell you my theory about this thing. Always beware of any weird bug appearing in your ZFS. And I repeat, this is a bug. I think I will share these slides anyway, but there are these slides shared on I've given this talk several times, so they are still already available somewhere else. So you can have a look at this particular bug. It should be fixed or at least worked around as a default anyway. Always use the Postgres block checksums. Now Postgres 18 enables the checksums by default, so do it. Do not rely on, do not trust just one thing for your block integrity, because sometimes the file system says everything is fine, but it's not fine at all. So having an extra defense layer for your data integrity is always a good thing, and always use the right tool for the right job. Obviously, ZFS for a 20 megabyte database is definitely not the right choice. For a 20 terabyte database, it may be a good option for saving money and maintaining decent performance for your database. And always RTFM. And remember always that your mileage may vary. Now, a little thing about the storage, why the storage in the PostgreSQL ZFS worked better on GCP and slightly bad on AWS. When I delivered this talk at the ID Italy, Incontro DevOps Italia, this is the name of the conference, is the DevOps meeting, Italian DevOps meeting, a person after the talk approached me and said, oh, I know that ZFS performs very, very bad on virtual file systems. And that given me the hint of why it performed not so good on AWS, but incredibly good. I was surprised when I seen the results on GCP, because I suspect that GCP exposes the file systems as volumes, logical volumes, snapshot, whatever they are done, but they are exposing the physical devices to the virtual machines. Instead, AWS virtualizes easily the file system. In fact, they give different kind of file systems with limited IOPS, with the unlimited IOPS, depending. I remember it was GP2, GP3, and IoT2, if I correctly remember. And this affects massively the IOPS. So it's in fact a massively virtualized file system. And that probably is the reason why ZFS didn't reach the performance of the native file systems in Linux, because it was sitting on a virtualized file system. And yeah, at the end of this, this ends basically the presentation with 2 minutes to spare. So I hope that was interesting, and yeah, I'm ready for taking any question.
That was great, Federico. Do we have any questions? Anybody? You can put them in chat, or you can unmute yourself. That was a pretty complete talk. Lots of really good information.
No, otherwise I kill the audience. This is the,
no. Yeah.
This is something that happens every time when I do training online. And after 2 hours of me speaking for 2 hours without stopping, I say, okay, I killed you. I feel your pain.
Well, I don't think anyone's dead. We have proof of life from Scava, who sent us a thumbs up.
Okay.
All righty. Well, if there are no questions, I'm going to go ahead and wrap things up. Thank you again, Federico. That was a great talk, and I love all of the slides. Those were fantastic. Thank you also to PGX and PGUS. Coming up with SF Bay Pug, November 11th, we will be presenting It's All About Them Stats, Less Trouble with Casey Holston. And upcoming conferences are PGConf EU, which will be October 21st to the 24th in Riga, Latvia. We will send a link by email when the video is ready, and you can watch our social media. You can find us on LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are always looking for speakers, and we are scheduling for 2026. If you or someone you know is interested, you can contact us through Meetup. Thank you to everyone who came today. Thank you again to Federico. Always great seeing you and always great talks. Thank you so much. And we will see everyone next time. Have a great day and bye.
Thank you very much.